informal online seminar. And so today's speaker is Yusuke Oka, who is a PhD student of University of Tokyo in Japan. So he is talking about quenching for axisymmetric hypersurface under forced mean curvature flows. Okay, please.
Okay, thank you for your kind introduction. First of all, I'd like to thank Professor Mitake and Professor Tran for inviting me to speak here today. Today's my talk is based on the joint work with Hiroyoshi Mitake and Han-Bin Tran. I've just thanked. Okay, let's get started. In this talk, we consider the motion of hypersurfaces gamma sub t immersed into the Euclidean n+1 space evolved by a forced mean curvature flow. V of xt is equal to kappa of xt plus f of x for the point x in the hypersurface gamma sub t. Here, the v of xt denotes the normal velocity at x, and the kappa of xt denotes the n times mean curvature of the hypersurfaces at x. And here, f is a given function, and we call it the forcing term. And t is a parameter, and we think it as a time variable. We assume that the hypersurfaces gamma t is axisymmetric. I mean, the gamma sub t is described as follows. The set of point x, xy in the r times rn, the magnitude of y is equal to the sum function u of xt. Here, u is a non-negative value function, which is unknown function in the next and subsequent slide. In response to this setting, we also assume that the forcing term f of xy is independent of y variable. F is only depends on x. In this setting, we calculate the normal velocity and mean curvature by use of some elementary vector analysis formula. And we obtain the following Cauchy problem. For the simplicity, we always consider the hypersurfaces in the periodic setting. I mean the spatial variable x in the flat torus T, which is defined as follows. Okay. So we get the following Cauchy problem. The time derivative of the unknown function u is equal to the uxx over ux squared plus 1 minus n minus 1 over u plus the f of x times the square root of ux squared plus 1 for x in flat torus, and t is positive. And this is Cauchy problem, so we think we take some function as initial data, g of x. ux0 is equal to g of x. Here u is unknown function. And we always assume the assumption A1. The forcing term f and the initial data g is both of this is positive valued function on torus, and they are smooth enough. Okay. And we use the following notation, and the f bar and overlying of f and underlying of f as the maximum and minimum of f, and same one. And we use the same notation as g. Okay. Next, I introduce the quenching phenomena, the notion of the quenching phenomena. In our problem, we can use the comparison principle, and the comparison principle preserves the order of gx and the constant zero function. So our solution u of x is always positive. And this means that as long as u is exist. So we can meaningfully define the following number t star, the supremum of t, positive number t, the infimum of u of xt over x in torus is positive. Of course, it is in the open and closed interval 0, infinity. And this number depends on initial data and forcing term.
Yusuke,
Hey.
maybe it's better to write your image picture to
Image picture.
explain.
Yes. We
Because the
consider
situation, yes.
We consider the graph expression of the hypersurfaces. So in a general setting, not so good picture, and the family of gamma t immersed in Rn plus 1. But in this setting, we the hypersurfaces gamma sub t is expressed as follows, like this. As the graph of some function u of x. Yes. Of course, it is flat torus, so
Right.
it is the same value.
Right. Okay, go ahead.
And here, the image of quenching phenomena is like this picture. So the initial state g of x, and it's evoluted into like this. Down, perhaps it downs, and there is a possibility that the infimum of this function u of xt reaches the 0 point. So we call this like this phenomenon. We call this phenomena as quenching. And okay, and we call this quantity t star the quenching time for our problem P. And we say that quenching occurs if the quantity t star is is positive number less than infinity, and quenching does not occur if the quantity t star is equal to infinity. Here is our aim, today's aim, and the aim of our paper. We want to study this phenomena, quenching phenomena, in terms of the competition between the forcing term f of x and the mean curvature of the initial datum g of x. Okay. This aim is the same as in the previous slide. To see this, okay. To see this, we introduce a small scaling parameter epsilon as follows. We put the inverse of the epsilon as the coefficient of the forcing term, and we put the epsilon to the power of alpha as the coefficient to the initial data g of x. And we aim at observing the quenching phenomena, quenching behavior of p epsilon in light of these scaling factors. If we take epsilon is equal to 1, it's coincide with the previous one. Here. Here, t star epsilon is quenching time for this problem P epsilon. Now, let us think naively. For small epsilon, if alpha is bigger than 1, the the curvature term at the initial time is stronger than the forcing term. And if alpha is smaller than 1, the curvature term is weaker than the forcing term. Taking into account that the curvature term induces the quenching phenomenon and the forcing term plays a role in preventing it, we can expect that the quenching happens if alpha is larger than 1 case, and the quenching does not occur if alpha is less than 1 case. Indeed, we are able to justify this intuition by constructing some super or subsolutions to our problem, P epsilon. This is one of our main results. And here, summary of our quenching or no quenching result. Maybe I've just explained about and perhaps I repeated, but if the alpha is larger than 1 case, the quenching phenomenon happens. If for sufficiently small epsilon, and the other case, the quenching does not occur for sufficiently small epsilon. This is shown as in proposition 1. And for the case of alpha is equal to 1, the critical case, the relation is important. Indeed, the product function f of x times g of x plays an important role. In fact, we can show this type result. Okay, I will explain later. Okay, and go to the next slide. And in the first half of today's talk, our goal is to give a proof of this table. And in the latter part, we will discuss the locations of quenching. Okay. Let's begin with the alpha is not equal to 1 cases. Here, our first proposition. Assume A1, the smoothness of the focusing term and initial data, and the positivity of the two function. And let epsilon and alpha is positive number, and u epsilon be the solution to our problem P epsilon. And let us denote T epsilon stir be the quenching time for our problem P epsilon. Then there exists some number epsilon 0 larger than 0, such that for all epsilon is in the open interval 0 to epsilon 0, if alpha larger than 1, then the T star epsilon is finite. I mean, the quenching occurs. And if alpha is less than 1, then the quenching does not happen, can never happen. Okay. We will show this proposition by some ODE analysis. I think that it is a little bit easy, but important. Okay. I explain. First, we fix some positive numbers A and B. Then consider the ODE of this form. Of course, this is an associated equation with our PDE. If we think of a spatially constant function, uxt is uxt is equal to yt. So we can drop off the derivative of ux, a derivative term, ux and uxx. So we reduce this ODE. Okay. Let's see the derivative of the solution y prime 0. Let's think the signature of the y prime 0. We put the initial data. We put the initial data here. So we have this quantity, and this is negative if we assume that alpha is bigger than 1. Indeed, -1 is equal to and so it okay. So the important thing is the so the signature of this quantity is determined by the epsilon to the power of alpha and versus the epsilon 1 to the power of 1. And if we assume that alpha is larger than 1, as in the epsilon, the limit of epsilon to the 0, this term is stronger than this term. So the signature of this quantity is negative for sufficiently small epsilon. And the other case, if alpha is less than 1, the y prime of 0 is bigger than 0 if epsilon is sufficiently small. So this observation implies the monotonicity of y of t in the neighborhood of t is equal to 0. Thus, if alpha is larger than 1, then the I should write y prime t. The y prime t is by definition here is equal to this quantity, and by the monotonicity of yt, this quantity is evaluated by this, and this is the same one as in the previous slide here. So this is a negative value. And also the other case, this quantity is positive for all t, positive number. Therefore, if the number epsilon, or parameter epsilon, is sufficiently small, we obtain that y of t is strictly decreasing if alpha is larger than 1, and y of t is strictly decreasing if alpha is less than 1. I should write alpha less. Okay. So from this observation, we can construct some simple super solution or subsolution as the spatial constant function. In the case of alpha is larger than 1, taking A is equal to the maximum value of f, and B is equal to maximum value of initial data, we obtain a super solution V epsilon xt is equal to y of t to p epsilon. I mean, because the y of t is calculated as follows. T, and this is larger than y t xx plus y squared. Because this quantity is equal to 0, we can put this term and minus plus the maximum value of f is trivially larger than f of x. So, sorry. And also y of 0 is maximum t. Oh, sorry, I forgot the epsilon alpha and maximum t3, and it is larger than epsilon to the power of alpha times gx. So this v epsilon gives a super solution of our problem p epsilon. Okay. And so and we can calculate we can calculate the v of epsilon y of t explicitly by simple calculation, and so we can deduce that there exists a number t sub epsilon tilde such that the v of epsilon x t epsilon tilde is equal to 0 for all x. So but by a comparison principle, we get the inequality here, and u epsilon is our solution, and v is here. For all x and t is in torus, and this interval, this represents the minimum of this quantity. So combining above the two plane, we can deduce that u epsilon quenching in finite time. And in the case of alpha is less than 1, taking a and b as follows, we obtain a subsolution. And also we can calculate the yt explicitly, and we can deduce that there exists c, and c such that c is less than y and less than our solution u of epsilon. So in this case, the quenching phenomena never happen. Okay. Hereafter, we always assume the alpha is equal to 1. Okay. 26 minutes. Okay. Okay. The case of alpha is equal to 1, the situation is more subtle. And this is the same one as in the previous slide. And here is our main theorem. The claim is that assume A1 holds and assume alpha is equal to 1, and u epsilon is the solution to our problem. And there are two claims. The one is if the product function fx and fx times gx and its minimum is larger than n-1, then there exists some epsilon 0 and c 0 such that this relation holds for all x in torus and t for t, and for all epsilon is in the open interval 0 and 0 epsilon 0. In short, for sufficiently small epsilon, in this case, the quenching phenomenon does not happen. That is, the t epsilon star is equal to infinity. And the second one is if the max of the f and f times the max of the g is less than n minus 1, then for all epsilon, the quenching happens. That is, T epsilon star is less than infinity. By the way, these two claims seems a little less symmetrical. This is not the same one, not so well correspondence. How about the case of the maximum of the product function f g is less than n minus 1 case? How about the case? How about this case? Although it is difficult to give an answer, but we have one suggestion. It is the next slide. We introduce a notion of the quenching in the limit of epsilon. We call the epsilon limit quenching. Here is the definition. And alpha is equal to 1 and u epsilon, the solution, is same. Definition is here. If there exists some sequence of parameter e epsilon sub k with epsilon sub k goes to 0 as the k goes to infinity, and there exists the sequence of points xk and xk tk in the torus times the open interval 0 infinity, such that the u epsilon k of xk tk over epsilon k goes to 0 as the k goes to infinity. Then we say that epsilon limit quenching happens. And the second theorem of our second theorem is about epsilon limit quenching. The claim is here. Assume A1 and A1 holds and assume alpha is equal to 1 and u epsilon is the solution to our problem. If this condition holds, the product of the maximum of product function is less than n minus 1, then epsilon limit quenching happens. This phenomenon happens. Okay. Okay. I will now I will give the proof of these two claims. First, I will explain the proof of theorem 1. No quenching and quenching result. The first one is proved by subsolution method. We construct some subsolution, and before then, we rescale the problem. We setting v of epsilon as follows. We put the inverse of epsilon time as the coefficient of a solution u epsilon xt, and we rewrite our problem p epsilon as follows. Then we begin the proof of the first claim. By the assumption, the minimum of the product function is larger than n minus 1 assumption. So there exists delta small. There exists some positive number delta such that this inequality holds for all x in torus. And then we can prove that this function psi of x is defined as n minus 1 over fx minus delta is a subsolution to this equation. We can prove this, and I will explain. And first, it is clear to see the initial data. About the initial data, psi epsilon is less than g of x, and this comes from this observation. And so all we have to do is check that this function satisfies the equation in the substitution in in the subsolution sense. Okay. It is done by direct calculation. Indeed, the we split it to explain, we split it into two parts, and the left hand side is estimated by the psi of xx, and our assumption of the function f is smooth enough, so we can say that there is some constant. And the right hand side is calculated as follows, and this term is larger than 1, and f of x is positive, so this is less than, this is larger than delta. And so we can take some epsilon 0, we can deduce that C of delta epsilon squared is less than delta for sufficiently small epsilon. So we can say that our psi is a subsolution to our problem, discrete problem 5, for all epsilon small enough. Therefore, by using of comparison principle, we obtain that the u epsilon over epsilon is estimated below by our subsolution psi of x, and this is estimated by its minimum, and this is trivially constant, positive constant. So this estimate implies a conclusion. No, in this case, the quenching never happened. Okay, and then second claim, and this is almost same as in the proposition 1. Recall our assumption. If we assume this assumption, we can also construct a specially constant super solution, which goes to 0 in a finite time. Indeed, if we set and this is same ODE as in the proof of proposition 1. If we set A is equal to maximum of f and B is equal to maximum of G, and we can calculate, we can solve this ODE explicitly, and note that at the initial time, the y prime 0 is less than 0, so we can say that y is strictly decreasing, and by similar argument in the proposition 1, we can say that T epsilon star is less than infinity, and in this case, the quenching phenomenon happens. Okay, and from now, we begin to prove the second theorem, the epsilon limit quenching theorem. To prove this theorem, we have to establish an a priori estimate on the derivatives of the solution. Although I wrote the full proof in this slide, but I don't have enough time, and I think it's a little bit standard method, so I will give somewhat abbreviated explanation, and this is a priori estimate, and this claim, the claim is if there exists some positive number C star such that our solution U epsilon x0 is larger than epsilon times C star for xt, then for all natural number k, there exists some positive constant independent of epsilon, such that the derivatives of our solution U, the time derivatives, epsilon times the time derivatives of U epsilon plus the U of the spatial derivative of U is estimated by C, this C, for all xt in this zone, x in torus and t is in this interval. We split the proof into two parts. I mean the time derivative parts and the spatial derivative parts. The first one is the estimate of time derivative of u time derivative of u epsilon. To prove this, we define some auxiliary function psi plus minus by this form. This is constructed by the initial data and plus minus the linear some linear term, and indeed we can check that this is super and subsolution in the short range of time, and by use of this we can deduce that, sorry, I skipped. We can deduce that the time derivative of our solution and at t equals 0 is estimated by above by c1 over epsilon. And next, we differentiate our problem p epsilon with respect to t and set this function, the time derivative of solution, to this equation. And now we again construct some super or subsolution in this form, exponential form, and we can check that these two functions are super and subsolution to this equation of our time derivative, the equation of the type of derivative. This is super and subsolution. And then we get the conclusion by comparison principle. This psi minus is less than ut epsilon, and psi plus 5 plus. Okay, 10 minutes left. And the next one is estimated of u and the spatial derivative of u. And this is the estimate of spatial derivative is done by the Bernstein, so-called Bernstein method. So we differentiate our problem P with respect to X and multiply this product, this equation, by the spatial derivative of U, and set this psi to 1/2 or 1/2 times the ux epsilon squared to obtain this equation, and assume that this psi, the maximum of this psi is attained some point x0 and t0, and we have the we have these relations. The spatial derivative of psi is at this point is 0, and time derivative is larger than 0, and the second derivative of psi is less than 0. Therefore, at this point, we by use of our equation, we can deduce such kind of inequality, and moreover, we do some a little bit complicated calculation, and by using Young inequality, and combining these results into combining all, and we obtain this kind of inequality. And then finally, summing up, we obtain that the u sub x epsilon to the power of 4 is estimated by the ux epsilon to the u of x ux epsilon squared plus c for some c which is independent of epsilon. Therefore, we can deduce that the derivative of the u epsilon is bounded for some c. And by use of this, we can give the proof of theorem 2, the epsilon limit quenching result. Here, I rewrote our main result and go to the proof. And the proof is done by the contradiction argument. I mean, and therefore, we suppose that there exists the sister such that u star xt, sorry, this may be epsilon. The u epsilon over epsilon is estimated by sister for all xt and for sufficiently small epsilon. As before, in the proof of main theorem 1, we can show that there exists delta such that this type of function is a super solution to our problem P. And then we descale, we put the new function w epsilon as this form. And this function w epsilon satisfies these relations. The zero, the w epsilon is larger than sister, is by definition, and w epsilon is estimated by this function. This is comparison principle, and this is trivially estimated by some constant. And the time derivative of w epsilon is equal to the epsilon times the time derivative of u epsilon, and we just proved the a priori estimate for family of solution u epsilon. So there is some constant c for each k. And then we want to show that this family of w epsilon goes to some limit function. I mean, formally, oh, sorry, I forgot to write the equation that our w satisfies. And anyway, formally, we can imagine that the limit equation, the limit function w epsilon satisfies this kind of ODE as I met the similar one. Then this is ODE for if we fix spatial variable x fixed for each x, and this is ODE. And we want to show that the convergence in some sense. So we introduce some viscosity solutions with some terms of viscosity solution framework. So we define the half reduced limits of W epsilon as follows: W upper star and W lower star. This is defined as follows. I think it is a little bit standard. And because we have a priori estimate of W epsilon in the previous slide, this is estimated by C. So we deduce that the W upper star and W lower star is in Lipschitz, the local Lipschitz function for all x fixed. And now by use of the stability of viscosity solutions, and also thanks to the uniformly bounded W epsilon is uniformly bounded, so we can use the stability theorem of viscosity solutions, and W upper star and W lower star are viscosity sub and super solution to the limit ODE. And also, thanks to the Lipschitz continuity, maybe I don't have enough time. And we can show that W upper star is less than W lower star by the comparison principle in the version of the viscosity solution. Therefore, we get this is equal, and we write this W, and thus our W epsilon converges to W locally uniformly on here as epsilon goes to 0. So
Okay, Yusuke.
Hey.
Your talk will be almost over. So maybe you can say something more on the quenching place
yes.
and just explain your result. Okay, not
Yes,
the detail. Just explain what did you get.
Okay. And the latter part of this slide is about locations of quenching, and the next aim of our study is to study the locations where the quenching happens under an additional symmetric condition, A of 2. This is the F and G satisfies this condition for X and this condition for X here.
Okay, maybe better to write
I write the picture, and 0 and 1 it is narrow, and 0 and 1 half. The F and G is like this, and F or G, and they are even at 1/2, so like here, and extended into a whole real line periodically. Yes. This is an image of our assumption A2, and assume A1 and A2 hold, and assume that the maximum of F n times maximum of G is less than n minus 1. So this says that quenching happens. And then it holds that this limitation for all k in the integers the limit of u of kt is equal to 0 as t goes to the quenching time. And for all the other point x, the limit of u of xt is positive as t goes to quenching time. And this proof is spread into four steps, but I don't have time, so
Yeah, but
skip.
what's the
Yes,
point?
Point is
Key point.
it is essential to in this also in this proof of theorem 3, the a priori estimate is essential. And we construct some uh, we construct some uh, we construct some subsolution like this form, and subsolution of the derivative of u this form, and we integrate it a to x, and we get this relation, and we can deduce that this claim. And here, and we can thanks to the a priori estimate, that our solution u is Lipschitz in this as function defined in this area, and so we can replace limit lim and limits with limit in the above because u is Lipschitz. And so I didn't explain, but as like this, we can obtain the positivity of the limit of u of xt, and as t goes to the quenching time for all x in 0. Sorry, this is the semi-open interval of 0 to 1/2. So this says that the quenching profile is like this. So we call it the a single point quenching result.
Mhm.
Okay.
Okay.
Sorry
Good.
for the time. This is the last slide. Thank you for kind attention, and sorry for my terrible English.
Okay, thank you, Yusuke. So it's now time to ask a question. So from the audience, do you have some any comment or question? Please ask by yourself. Free.
So can I ask one?
Sure.
So actually for this proof, so can I ask, like, since you already have the quenching at 0 and 1, so why not construct a barrier from 0 to 1 for u? Like why you consider the subsolution for the derivative instead of the original function from 0 to 1?
Yeah, this.
Right, yeah, that one.
Please say again.
Oh, sorry.
What's the question?
What is that?
So I mean, like, so it seems you can use this subsolution for the derivative. So like,
Yeah.
what are the reasons for not using it for the original solution u from 0 to 1? Since you already know the quenching at 0 and 1.
Original. I don't know.
Yeah, I can translate. So a quick question is very natural, right? I mean, why don't you construct the sub-solution for U itself?
So, anyway, my proof is correct, and so equation. Yes. So,
Maybe we can save this for informal discussion later.
Yeah, that's a good
sorry.
idea.
It is like the method in the literature. To conduct our study, I did some literature, and in some literature, someone construct
This is
the
not
solution.
no, this is not a good answer.
Yes,
Could
I think so.
explain.
Sorry.
Okay. Other question? Comment?
Maybe I can ask a quick question.
Yeah, sure, please.
Yes. So I think probably you have already thought about this, but I think you can also do more general curvature flows like power curvature flow. Have you ever thought about this? At least at the beginning, I think in the proposition 1, basically you talk about this curvature effect and this driving force effect. Basically, you want to compare which one is bigger. But you basically can change this curvature term to more general curvature, like a power of the curvature. It should still make sense, and the argument should be almost the same. So I guess many of the results probably can be extended to more general cases. Is it true? I think maybe the theorem 2 would be a little bit more complicated in general case, but yeah.
Yes,
Yeah,
I think so. And the important thing is to use the comparison principle.
Yes.
I
yes.
agree.
Yes. Yes, that's my impression. Yeah.
Yeah, thanks for your question. Yeah, that's for sure. It's another problem, and if it is a critical case, then there should be other difficulty appear.
Right. Yeah.
Yeah.
Anyway, thank you. Thank you.
If it is not the critical case, I think it's maybe that's a simple modification by using ODE. Yes.
Yes.
At least we can easily see quenching happens or not. But the critical
I mean, at least formally you can see, right? Yes. Yeah. Okay. Yeah. Thank you.
Okay, so this is a kind of a formal question time. So let's thank Yusuke once again. And okay, let's stop the record.